So this is the final example that we're going to look at tonight. This is the EX29 project in my Java 8 folder in my Live Lessons GitHub repository. And this example shows how to combine Java sequential streams and Completable Futures framework to generate and reduce random big fractions concurrently and asynchronously. And it also demonstrates the lazy processing semantics of both Java streams and the Completable Futures frameworks. And that's kind of cool. So in this case, we're going to have 10 big fractions we want to process asynchronously in a stream. And then we've got a main program that keeps printing various diagnostics along the way. And that'll give you a sense of when work actually gets done versus when things are set up to be done later. So the first thing we do is we go ahead and make a list of random big fractions. And here's what it looks like. We use the stream generate factor method to make an infinite stream of random unreduced big fractions, except we're going to limit that to S-mass fractions, which is 10. And we're then going to trigger the processing and collect it into a list. Here's make big fraction. This creates potentially absolutely gigantic big fractions. We use the big integer features with random number generator to generate a large random big integer that goes up to 2 to the 150,000th minus 1, which is an absolutely enormous number. Big integer, of course, is an arbitrary precision integer class. Then we create a denominator that's going to take that giant numerator and divide it by a number from 1 to 10. And then we make ourselves a big fraction that will either be reduced or non-reduced with the numerator and denominator that we define. Okay, so now we have a list of big fractions, and we go ahead and print that list out, and that will actually print out right there because we did that all synchronously. The next thing we do is we go ahead and make a big fraction stream. So we take that list of big fractions, and we turn it into a stream, and this stream is going to be a stream of completable futures to big fractions, because for every element in the stream, we're going to reduce and multiply it, or I guess reduce it asynchronously. So here's what we do. Here's the reduce big fraction async method, which will use the supply async factor method to start this supplier lambda in a background thread in the common fork join pool. And that will go ahead and take the big fraction and reduce it. And then we print out what was reduced and we return the big fraction. And that's all going to take place in the background. But this is a stream, and nothing's going to start running yet. We just have a stream of completable futures to big fractions. We have not hit a terminal operation, so nothing has begun to run. What we then do is we're then going to call another method called make completable futures stream. So you see, we first made a stream of completable futures to big fractions, and now we're going to make a completable future stream, which will be a single completable future to a list of big fractions. And this should look very familiar by now because this is basically the same algorithm we looked at earlier that is what we used for the futures collector, and also we used for the stream utils join all method when we looked at the earlier example. So what we do here is we convert the big fraction stream into an array. Believe it or not, you can take a stream and turn it into an array, just like you can take a list and turn it into an array. So we end up with a completable future we end up with an array of completable futures to big fractions. And then we use the all of method in completable future, passing in this array of completable futures. And then we do what we've always done. We go ahead and convert the list into a stream, use the map method with completable future join, which never blocks. And then we collect the results into a list. And just because I wanted to have a place to put a diagnostic, I have a method call here called getListCollector, which prints out that it's in the list collector, and it just returns the list collector. Okay, so that's what we're doing in that method. So we're going to end up with a single completable future to a list of big fractions. Again, nothing is actually running at this point. So we demonstrate that by printing out that we're right after the call to make completable future stream. And then just to take it one step further, we're going to create a completable future to avoid result by calling then compose, on the sort and print list async method. And the sort and print list async method is also super clever. What it does is it takes the list of big fractions that we have at this point after collect returned, after all the asynchronous processing was done to do the reductions. And then we go ahead and create two completable futures. Should probably use vars here again, just to be a little bit more concise. So we're going to quick sort the list and we're going to heap sort the list at the same time in parallel. And then whichever one finishes first, we're going to take that result and we're going to print it. And here's what print list does. It just goes through and prints all the values out. So this is a super clever way of being able to leverage the proliferation of cores on modern multi-core processors by just running all the sort algorithms at the same time and just letting God sort them out. And whichever one finishes first, that's the one that's going to be used to print the results. We then print that we're done with then compose. Still nothing will have been printed out. And it's not until we call the join method here that everything starts to run. So at that point, we're up and running and the computations will take place. And then all the computations will run. And then at that point, we'll get all the results. And then we print that we're done with the whole program. So let's go ahead and take a look at what happens when we run this program. And you'll see it goes off and chomps away for a little bit. As you can see, it creates absolutely enormous big fractions. It goes on and on and on because they're very large. And this is what they are initially. You can see they're not sorted in any particular order. Then after the print list call, we call the first map call and make big fraction stream. Then we call the collect call and make completable future stream. Still nothing is printed out. Then compose is called. Still nothing is printed out. And it's not until we call join that something is going to be printed out. So I should probably actually say after then compose and before join. And at that point, when join is called, that's when all those things get reduced. And then you can see here that the get list collector method gets called. That's where collect actually takes place. And at that point, then we've got the sorted results from that sort and print list method that we looked at. So very, very interesting set of results here. Let's say print after then compose and before join. So that's going to take place here. So that's an example demonstrating combining completable futures with Java streams, number one, and also showing how lazy Java streams and completable futures are. They don't actually do anything until they have to. And they typically do stuff when joins occur and or when collect gets run. And so that's how the whole program starts to work.